Welcome to the debate. We are diving into what is arguably the most critical strategic challenge facing longstanding C++ organizations today, really navigating the future of the massive Boost C++ libraries now that we are firmly entrenched in the modern C++ era, C++ 17, and, well, beyond. Our source material outlines a thoughtful modernization path, recommending a phased strategic migration, coupled with something they call strategic containment.
And that measured approach is exactly where the strategic challenge lies, I think. I believe the core disagreement is whether this containment strategy is sufficient or if the accumulating technical costs, what we're calling the productivity tax, imposed by the Boost ecosystem, is just so substantial that it warrants a much more aggressive, near total deprecation. We need to prioritize, guaranteed stability over marginal feature advantage.
Right. I fully agree that the costs are real. And that's precisely why the strategy is disciplined modernization. I support strategic containment as the optimal, pragmatic path forward. We absolutely have to get rid of the external dependencies that have become completely redundant because the standard library has finally caught up. But we must formally manage and retain the use of those essential, high-value Boost components that still give us a competitive edge.
But the issue isn't just one of redundancy, is it? It's the continuous drain on developer resources caused by the very nature of the ecosystem itself.
That's true. But let's talk about the unique value Boost still delivers. We're talking about libraries that fundamentally change our engineering capabilities. Boost.Asio for high-performance asynchronous networking, which abstracts away massive platform complexity. Boost.Graph for specialized graph theory and network analysis, a domain where standardized solutions are pretty much non-existent, and Boost.Spirit for generating advanced, high-speed compile-time parsers. The C++ standard offers absolutely no equivalent for these tools. By migrating the low-hanging fruit, libraries like smart pointers, optional, variant, and file system to STD equivalents, we immediately achieve measurable benefits like reduced compile times and improved code clarity, while preserving that unique advantage. It's the ultimate balance of risk reduction and feature retention.
See, I come at it from a completely different angle. That containment strategy, it fails to address the ongoing burden of the productivity tax because it focuses on capability, not sustainability. The total cost of ownership, or TCO, the cumulative long-term expense of maintaining, updating, and debugging these dependencies is simply too high. It demands a policy of aggressive deprecation that goes way beyond what the source material suggests, even for those specialized, unique libraries.
You cite technical overhead, but the data suggests that overhead is continuous and substantial only when using the template-heavy parts that have been superseded by the standard. We are targeting those specific libraries for removal.
I disagree that the overhead is limited only to the parts being retired. The cost is truly ecosystem-wide and continuous. We are talking about notoriously long compile times due to Boost's heavy template usage. Yes, even in unique libraries like Boost.Spirit, we have to factor in the cryptic compiler errors that dramatically raise the cognitive load for junior and even mid-level developers. And crucially, there is the significant maintenance overhead caused by Boost's API instability. The source material is unequivocal. Boost offers basically no promise that the APIs they rely upon will be stable. You are signing up for ongoing, high-effort maintenance simply to keep pace with an external project's evolution.
Okay, that instability is certainly a challenge.
It's more than a challenge. It's a strategic liability. Boost is a federation of over 180 distinct projects with uneven quality and maintenance levels. Relying on unmaintained or inconsistently supported libraries creates a massive long-tail risk that, over a decade, will vastly outweigh the benefit of those complexity-reducing tools. Our long-term strategy must favor alternatives that explicitly guarantee long-term API stability, such as Google's Absl library, over the high-churn environment of Boost.
You raise a critical point about overhead. But if we look at where that overhead truly originates, specifically the compile time, the data tells a story of redundancy, not core component use.
Compile time the ways are the ultimate developer drag. They slow the feedback loop on every single build, driving up continuous integration and, well, cloud build costs. Why do we accept this fundamental structural drag, which developers often call a pure nightmare, just for unique features that might only be implemented in, isolated corners of the codebase?
That's a powerful argument. And I acknowledge the frustration, but let me reframe the evidence slightly. We need to look closely at the WIT, that's W-I-T-T-Y, Web Toolkit migration case study. This organization moved from relying on many Boost components to using standard library equivalents. That study clearly demonstrated that the largest source of compile time overhead came from the components that are targeted for replacement in the strategic containment plan, smart pointers, Boost, any, and the like.
But what does that really prove?
It proves that our containment strategy is surgical. We are eliminating the overhead caused by redundancy while deliberately retaining the high ROI specialized tools. Retaining Asio, for example, avoids months of specialized asynchronous networking engineering effort that would certainly dwarf the compile time costs of using the library. The drag you are worried about comes from the general-purpose template-heavy components, and those are the ones we are removing. The solution is a targeted fix, not a wholesale abandonment of best-in-class tools.
I accept that the W study showed improvement by moving away from Boost's implementation of now standard concepts.
Right, but that doesn't solve the fundamental problem. The general philosophy of template-heavy design inherent in those Boost components we are keeping remains a liability. I agree, the philosophy creates overhead, but we mitigate that overhead by isolating the libraries that follow that philosophy. Let's maybe pivot to API stability, because that's the second pillar of your TCO argument. Boost's historical role has been the proving ground for innovation for C++. When you are innovating, API volatility is expected, sure, but the permissive BSL 1.0 license makes it highly commercial friendly. The proposed containment strategy directly mitigates that volatility risk. We establish a new internal coding standard, we pin specific, well-tested versions of the contained libraries, and crucially, we build internal, thin wrappers to insulate the bulk of the codebase from those direct Boost APIs. This is a robust mitigation plan built on standard engineering practice.
I'm sorry, but I just don't buy that the answer to high maintenance is more maintenance. Stability should be an inherent feature of the dependency, not a risk we have to mitigate using bespoke internal wrappers and rigorous version pinning. That wrapping process is internal technical debt. We are creating a new internal dependency with zero community support, essentially duplicating the Boost maintenance burden inside our firewall every time Boost has a major version shift.
Well, it is a one-time cost to gain insulation and control.
It is not one time. It is ongoing adaptation. Compare that to Google's Absl. They explicitly commit to long-term API compatibility and even provide tooling to manage updates if a break is necessary. Why should we accept the ongoing high-maintenance cost of adapting to Boost's breaking changes, which can be non-trivial, when alternatives offer a guaranteed reduction in long-term TCO? Furthermore, that 2023 security audit was frankly sobering, confirming that security maturity strongly varies from library to library across that massive collection. Version pinning is a complex management challenge when dealing with a federation of 180 projects, not a full solution to internal security variant.
Look, I won't deny that the security audit was sobering, and the need for internal rigor is paramount. But that audit just proves we need tighter control, not wholesale flight from indispensable tools. While Absl's commitment to stability is excellent, it has significant functional gaps. You mentioned Absl as a full alternative, but can it replace Boost.Asio? No. Absl is focused primarily on concurrency and utility types. It doesn't solve the functional deficit we face in networking, graph theory, or advanced parsing.
That assumes there are no other viable alternatives that don't come with such heavy baggage. That's a compelling argument regarding the functional gaps. But have you considered alternatives outside of the standard library and Absl?
Which, specifically?
Well, let's look at Q-Core. It provides a cohesive, object-oriented framework for networking, file system, and system utilities. It significantly overlaps with Boost's general offerings, but is famous for superior API consistency and predictability. It generally leads to faster compile times and far clearer error messages precisely because it avoids the heavy template machinery in its core components. Why not adopt these battle-tested, consistent alternatives for unique needs instead of accepting the instability and complexity of Boost?
That's a great point about Qt, and I absolutely acknowledge its API consistency and clearer error messages. However, the trade-off is architectural flexibility. Qt favors a strict object-oriented design paradigm, which is far less generically applicable than Boost's template-based approach. We would be sacrificing the ability to write highly generalized, zero-cost abstraction code, a core strength of template metaprogramming in C++.
But the architectural trade-off is magnified when you consider the ecosystem cost of Qt itself. Adopting Qt means adopting their build system, QMake, or wrestling with complex CMake integration just to pull in a utility. That is its own massive layer of technical overhead and organizational friction.
Exactly. The choice isn't simple. But when we look at truly specialized domains, Qt, or frankly any other mainstream library, simply doesn't compete. For graph theory, there is no standard or mainstream alternative that rivals Boost.Graph. Even Folly, another highly respected hyperscale utility library used by Meta itself, has a documented dependency on Boost for certain complex features. For the highly specialized tasks we rely on Asio, Graph, Spirit, Boost remains the best-in-class battle-tested solution. Discarding it is discarding a significant competitive advantage just to achieve marginally cleaner error messages.
I disagree that it's marginal. The technical friction is a continuous drag on developer velocity. While Boost might be the gold standard for Graph, the strategic choice boils down to this. Is the marginal gain in the Graph library's flexibility worth exposing the entire engineering organization to the instability, the cumulative productivity drag, and the security variance confirmed by the audit associated with the entire ecosystem? An ecosystem that is, let's be honest, suffering from thinning maintainer participation in many of its 180-plus component libraries.
That is precisely why the phased approach is the only rational strategy. We address the stagnation concern by eliminating the unmaintained redundant parts first, the 80% that has been superseded by C++17. We then only retain the small, actively maintained, and truly irreplaceable 20%. It's a surgical strike, designed to maximize ROI and minimize future technical debt by applying the right tool to the right problem.
And I maintain that the internal cost of managing that contained list, building those internal wrappers, dealing with version pinning complexity, and mitigating the security variances is still too high compared to a clean, definitive break. For organizations prioritizing resilience and long-term TCO reduction, a strategy centered entirely on the C++ standard and inherently stable alternatives like Absl is the only sustainable strategy.
The evidence, as I see it, overwhelmingly supports the phased migration strategy. We must get rid of external dependencies that have become redundant. The smart pointers, optionals, file systems to improve developer velocity and reduce build costs. However, we must simultaneously be disciplined enough to strategically manage and retain the irreplaceable, high-value components, Asio, Graph, Spirit, that continue to offer unique, production-ready solutions not present in the C++ standard. This is modernization, not abandonment.
I see why you feel strongly about retaining those features, but the data on continuous compile times, API instability, and the uneven code-base health highlights that the continuous productivity tax of Boost is simply too great to justify that containment. Even the unique features introduce hidden complexity and risk that a modernized codebase should strive to eliminate entirely. Complexity is expensive.
Ultimately, the source material shows that the strategic decision for any organization is a fundamental trade-off between maximizing the available feature set and minimizing long-term risk and overhead.
It really requires a nuanced library-by-library assessment to decide exactly where that line between indispensable utility and unacceptable cost falls for your specific engineering team.
And that is where our listeners must now weigh the evidence and determine their path forward. Thank you for joining us on the debate.